Hi, everyone. Welcome to the Wherobots live stream. My name is Will. Um, Let us know in the chat where you're joining from today. It's always fun to see folks joining from all over the world. And also, that helps me make sure that I can see the chat and let me know that folks can hear me too. Always a good, always a good test there. Cool. So today we are focused on looking at raster data with spatial SQL in Wherobots Cloud. So we'll take a look at what is raster data, how do we load different raster data sets, what are some use cases for analyzing these data sets using Sedona and Wherobots Cloud. So that's the goal for today. As always, like to keep these sessions as interactive as possible. So drop any questions you have in the chat. I'm monitoring the chat on YouTube and LinkedIn. So definitely let me know uh, as things come up, what you're interested in, what you'd like to see, and if you have any questions. And with that, let me share my screen and we will get into it. Great. So we're going to be using Sedona in Wherobots Cloud. If you've seen previous sessions on this channel, you'll know that Wherobots Cloud is a managed cloud platform for large-scale geospatial analytics. What does that mean? Well, if I have lots and lots of data with some geospatial components, we can work with that data using tools like Spatial SQL in a notebook environment to do things like join our spatial data together, visualize the data, prepare that data for AI pipeline. So Wherobots Cloud is based on the open source Apache Sedona project for working with large scale geospatial data. So I've signed into Wherobots Cloud here. Anyone can create an account. Let me drop the link to this in the chat. So if you'd like to follow along, anyone can create an account at wherobots.services. And once you create an account in Wherobots Cloud, one of the first things that you'll want to do is provision a notebook environment. Zoom in and make this a bit bigger, which I've already done here. You can see it says Open Notebook. The notebook environment is kind of the main interface for working with data in Wherobots and Sedona. And we typically use the Python API. We can also use Scala, but we're typically using Spatial SQL within that environment. And we'll see what that looks like in a moment. We can also do things like upload files into Wherobots Cloud. We're not going to really be doing too much of that today. We're going to use mostly public data sets, but it's good to know that that's included. And then we can also do things like schedule jobs to run periodically to fetch new data sets, crunch them as part of a data pipeline. So I'm going to jump to the notebook environment. I'll share the link to this code on GitHub. Actually, I'll go ahead and do that now. So this notebook is on GitHub. I'll just drop a link to this in the chat so you can follow along afterwards if you like. Okie doke. So what we're going to do today is take a look at working with raster data. First, we'll talk a little bit about what that is, how that compares to other geospatial data types like vector data and geometries. And we're going to look at how we can load raster data, specifically GeoTiffs we'll be working with today. We'll talk about some other file formats. We'll look at things like how do we tile large raster data sets to be able to work with tiles more efficiently. How do we do things like join vector data to our rasters? How can we do things like zonal statistics to calculate statistics or aggregate data for certain areas? We'll take a look at saving rasters to Havasu tables, map algebra, exporting GeoTiff. So a lot of the sort of foundational getting started working with raster data in Wherobots and Sedona DB. So to start off, we're importing some packages we'll be using, and then we're configuring our Sedona context. And here we're just configuring access to a public S3 bucket where I have some of our data stored that we'll be working with today. So to start off, let's make sure we're all on the same page here, and we'll talk about what exactly is raster data and how does it compare to vector data. These are kind of the two, at a high level, different types of data that we work with when we're working with geospatial data. So vector data, which we've worked with in past videos in this channel, vector data, we're typically some geometry, so point, line, polygon, and then a table of associated attributes. So I might have the polygon geometry that represents a country, and I might have the name of the country as an attribute of that. Or I might have point of interest data. So I have point geometry and like the name, category of a business, these sorts of things. With raster data, we're working with gridded or pixelated data. And I think one of the canonical examples of raster data, it doesn't have to be, but is aerial imagery. So in this example, this image is taken from Neon, which we'll be using a data set from Neon in a minute. So I think this does a good job of explaining what the basic ideas of raster data are. So if we have an aerial image, this could be a satellite image or something taken from a drone or an airplane, something like that. And each pixel, so the image is divided up into pixels, and each pixel has some value associated with it. In this case, we're looking at maybe just one band of data. So we can also have multiple values for each pixels. These are called bands. So in a typical aerial image, we might have 4 bands like red, green, blue, near infrared, something like that. And we have a value for each one of those bands for each pixel. Here we're just showing one band. And each one of those pixels, well, it has some coordinates in pixel space, right? So like the upper left is 0, 0 in pixel coordinates. But each one of these pixels also represents some real geographic area as well, right? So we have metadata associated with this raster data that maps our pixel space, so our pixels, to some real world geographic area. And rasters have a sense of a spatial resolution. So this 1 meter here is saying that each pixel represents 1 meter, 1 square meter of area on the Earth's surface. Then when we go to plot or visualize these rasters, well, typically what we'll do is combine multiple bands. So if we're going to visualize an aerial image, we'll combine RGB, red, green, blue values to be able to render that as an image. So that's the basic structure of raster data. How do we think about and how do we work with raster data in Sedona? Well, in Sedona, we have a table structure that we're typically working with as a database, and we use SQL to query that table. If we have a raster here, so imagine this is some Earth observation table, and we have a raster of here the United States. Well, typically we might tile that raster up into multiple tiles, and each tile is stored as a value in each row. So we end up with a Earth observation table with many rows. We have one raster per row, and we can also store some associated metadata alongside that raster, in addition to the pixel values, which will be stored in the raster column. But we might have the geometry that that raster tile represents, the name, an ID, some other associated metadata that we can store in the database as well. So once we've loaded our raster, what are some things that we can do with it? How do we analyze the data? What's the value that working with raster data can give us? Well, here's one example. There are many things we can do with raster data. Things like to calculate maybe some sort of vegetative index to tell us information about the land cover, maybe something like edge detection to identify roads, or run some machine learning models like classification, segmentation to identify objects. Um, but one common, I guess, common workflow, common operation that is at the heart of a lot of these use cases for analyzing raster data is this idea of map algebra, where we're actually looking at the values in each pixel, and maybe we're comparing or using values in a separate raster to compute changes in that pixel over time, or maybe we're looking at identifying uh, other bands where we're using the values of that pixel across bands to compute like a vegetative index, something like this. But here's a basic example of what this looks like in Spatial SQL. We'll take some hands-on looks at this in a moment. But here we're going to use the rs map algebra Spatial SQL function. So in Sedona, the Spatial SQL functions for working with rasters start with rs underscore. So we know we're going to be working with raster data. And here we have two rasters that represent average surface temperature of the Earth in 2 different years. And we want to subtract one from the other to get the difference, to see if there are areas where it was colder in this one year, if it was warmer in other areas. And to do that, we'll use this rs map algebra function where we pass in our two rasters, and then we do kind of a simple calculation here is raster 0 minus raster 1, looking at band 0. And that's going to give us a new raster that is going to be the difference in those temperatures. That's a basic example, but conceptually, we can see how we can use Spatial SQL, select from where, a similar pattern of working with SQL to work with raster data. Great. So let me zoom in a bit here, make this as large as we can. There we go. Maybe that's good. Great. So feel free to ask any questions in the chat. I'm monitoring it over here. Great to see folks joining and watching live. Great. So with that, let's take a look at a few examples. So I have 3 different examples that we're going to work through, 3 different data sets, and we'll see some basic use cases and ways of working with raster data. So the first is just how do we load a raster data set into Sedona? So Sedona supports reading a number of different raster data formats, the ArcInfo, Esri format, NetCDF, or GeoTiff, cloud optimized GeoTiffs. GeoTiff, I think, is one of the more common formats. So that's what we're going to work with today. And when we're loading a raster data set into Sedona, we have to make the decision if we want this to be an in DB raster or an out DB, so in database or out of database. There are trade-offs to these two approaches. An out-of-database raster, the OutDB raster, this is, I think, typically the more common use case, and this is typically what we want here, where we're referencing some remote file storage. So this could be like an S3 cloud bucket, something like that. And in the database, in Sedona itself, in our database tables, we're only storing some metadata and basically like a pointer to our remote data. So this is useful where we have very, very large raster data sets. We don't need to bring them all into the database to copy that data around. We can just have a reference to cloud storage and just store the metadata in the database. Compare that to NDB raster, where we actually are copying that data into Sedona, storing that in the database, or storing the actual raster data in the database. Um, this is typically not what we want to do. This can be useful where we have maybe data integrity or access efficiency considerations, but I think typically we want to work without DB raster, and all the examples that I have for us today are going to be working without DB rasters. So first, let's load a data set here. So we're going to load this GeoTiff from Wherobots examples S3 bucket, and we're going to do that using the rs from path spatial SQL function. And this is going to give us an outDB raster. And we can see here, if we print the schema of this table, we have just one column, which is our raster value. And we can do things like look at metadata for the raster with the rs metadata function. And so this metadata function is going to tell us things like what are the upper left coordinate of the raster pixels in geographic space. So this data set specifically happens to be in UTM. So these are eastings and northings. And the size in terms of pixels, so this is 1,000 by 1,000 pixels. The spatial resolution of each pixel. So in this case, this is in the units of the raster, which, because this is UTM, are meters. So each pixel is 1 meter wide and 1 meter high times 1,000. That means each raster image is going to be 1 kilometer. The skew, no skew, is the SRID. So again, this is the code for UTM, and then the number of bands. So in this case, we have 3 bands, RGB, which we could also determine from RS number bands. Tells us, yep, we have 3 bands. When I should say this data set, comes from the Neon high resolution camera imagery data set from the NSF that's used in a lot of ecological studies. This is, I think, flown from aircraft rather than satellite imagery. So it's quite, as you can see, 1 meter pixel is quite high resolution. We can visualize this data using rs as image. So again, we've loaded just one single image just to get started as a good getting started point. We'll work with larger scale raster data set in a minute here. So this is the scene we're working with. This looks like some forested area, a road perhaps, maybe, and then some dirt or glacial moraine, actually, I think is what this is. So we can get actual values of each pixel using rs values or the rs value spatial SQL function at a specific point. So here we are grabbing the value from the second band, which is the green band, at a specific point. So this point in the coordinate system of the raster, which in this case, this is just the upper left corner. And then I need to be able to be sure to set the SRID to match the SRID, the spatial coordinate system and reference of our raster, which is UTM zone 6, I think, in this case. And this, we could also do this for the red band. You could get the value in the upper left corner. That's not particularly useful. We'll see data sets where that actually maps to something meaningful in a moment. So let's take a look at a map algebra operation with this data set. So one thing that we can do with aerial imagery like this is compute these vegetative indexes. So NDVI is a common one. We don't have the near infrared band in this example to calculate NDVI. So we're going to calculate something similar, which is NDGI, the normalized difference greenness index, which is just looking at the normalized difference of green band to the red band. And we can do this using the RSMap algebra function. And it's quite neat with this map algebra function. We use this language called GIFL to specify the calculation that we want to compute. And this can be fairly simple, or it can be as complicated really as we need it to be. So in this case, we're going to calculate the difference of the green band and the red band divided by the sum of the green and the red band. So the normalized difference between green and red bands. And this is done for each pixel in our image. And then we're going to create a new view called NDGI. And it's important to note we end up with a new raster. This NDGI is a new raster, but it just has a single band. So we can look at the summary stats for this band. And the summary stats, these are going to be the count. So the number of pixels. So we have 1,000,000, so 1,000 by 1,000, 1,000,000 pixels. I think this is the sum, the minimum, the maximum, and standard deviation and average. So in this case, NDGI, basically the way we interpret NDGI is if the value is positive, that is indicating vegetation. If the value is negative, that is not vegetation. It's like rock or something like that. So we can inspect individual values at individual pixels. That will tell us something meaningful. So here we're looking at just the image in the upper left. I'd say the pixel in the upper left. So here in this kind of sandy, rocky area, and that value is negative, which is consistent with non-vegetative pixel. And if we pick another point, I think I picked a point somewhere over here, which is kind of in the middle of what appears to be forested area. And that value is positive, which is consistent with vegetative ground cover. So that's neat. What can we do with that? Well, we can export that data as a new GeoTiff using this rs as GeoTiff, and we can load that into another system. Okay, so that example, that was fairly simple, looking at a single scene, a single raster image. Let's look at a different data set now, loading multiple rasters. And in this case, we're going to look at some data from the uh, world climate, historical climate data. And so this is an interesting data set that has monthly averages from 1970 to the year 2000 of things like temperature, precipitation, wind speed, and then also things like elevation. So I downloaded the precipitation data set, and we're going to go ahead and load that. So this is now going to be multiple files. So we have one file for each month, and the month is the last two digits in the file name. So 01, that's going to be January, all the way up to 12 for December. So we're going to see a slightly different way of loading this data set. Rather than using the rs from path, we're going to load these using the binary file reader. And then we're going to convert that binary data into GeoTiff. And the reason I did this is we also want to bring through the path. So the path is what we're going to use to figure out which month that GeoTiff represents. And we're going to do that using a regular expression. So you can see here when we use the binary file reader to read each of these 12 files, we have the content, which is just a binary array of data, but then we also have the path, which is the file name that we loaded. So we can use the rs from GeoTiff function to pull in our binary data to convert that to a raster. And then we're going to use this regular expression, which just matches on the file name, looks at the last two digits, and casts that value to an integer to represent the month. And so this is precipitation data. So the average precipitation for each month from 1970 to the year 2000. And we look at the metadata. So this is the upper left. This is the width in pixels, the height in pixels, and the spatial resolution of each pixels in the units of our coordinate system, which is WGS84, which is degrees. So this maps to 10 arc minutes, right? 0.166667 degrees is 10 arc minutes. The skew, the SRID, which is 4326, the WGS84, and then the number of bands, just a single band here. So the value of each pixel is the precipitation fall for that month. We can calculate summary stats for the raster. So note here that we're getting these for each month, right? Because each raster represents one month of data. So the count, minimum, maximum, standard deviation. We can get the values for a specific point. So in this case, this makes a little bit more sense. So now for a given point, what is the precipitation for each month? Well, we can see not a whole lot of variation. Some months are rainier than others. May showers is the rainiest month for this area, it looks like. So when we have data like this, where the pixels represent some statistical value rather than maybe just like spectral imagery, this can be where zonal statistics can be useful. So zonal statistics, this is the process of taking some vector geometry. So maybe like the polygon of a city bounds or a county, a parcel perhaps, and joining that to our raster and taking all the pixels inside that geometry, and then calculating some statistics or some value for all the pixels that are contained within that geometry. So what we're going to do here is load the geometries of countries. So this data comes from natural Earth. So we have in this case, a shapefile that contains the polygons for the world's countries. And then what we want to do is calculate the average precipitation. So for all of the pixels within the bounds of each country, we're going to calculate the average precipitation for that country, and then look at that over time over the 12 months. So I should say, and one thing I forgot to take a look at here is the documentation for our raster functions. Let me drop this in the chat as well. This is a helpful resource. Cool. So this is the documentation specifically for working with raster data in Sedona. And we can see here we've worked with the raster loaders. We've worked with a few raster functions. You can see there are quite a few raster functions for working with raster data in Sedona. Many of these are individual operations for map algebra. So we saw the map algebra function, but we can also work with individual bands as arrays and perform the individual operations like compute normalized difference, subtract, divide, those sorts of things as individual functions on arrays of band values as well. We saw the raster writer data. So we saw writing that out to a new GeoTiff. And then what we're looking at now is map algebra, or we saw map algebra for calculating in NDGI in our case. What we're looking at now is zonal statistics. So there's two options. There's zonal stats all, which will calculate all of these statistical values for all the pixels within a given geometry. What we want to do though is look at just the average, so the mean of all the pixels for precipitation within each country. So we're going to use this rs zonal stats function to do that. And we can see here that the zonal stats function takes a raster and then a geometry. So in this case, the geometry is going to be the bounds of each country, and then our raster is going to be our precipitation data for each month. So let's see what that looks like. This is the schema of our country's shapefile. Here's the function that we're going to run. So here's our rs zonal stats call. So what are we doing? We're looking at from the precipitation table, grabbing the raster. So these are our monthly rasters, one for each month of data. And then from the countries table, the geometry of each country. So where the raster overlaps with that geometry. We're doing this for band one. We only have one band in the raster. We could do this for, if we had multi-band, we need to specify which band we want to work with. Then what statistic are we calculating? We're going to calculate the average. We want to know the average precipitation for the country. And then this last parameter, this is whether or not to ignore the no data value. So typically in a raster, if we have something like, I don't know, cloud cover, or if there's simply no data for a given pixel, we'll insert a value. Sometimes this is like minus 999. In this case, um, well, I know in the next data set we're going to look at it, the value is 255, but we're just going to ignore no data values. And then because we have 12 rasters here, we have one for each month. And what we're interested in is the sort of sum of the monthly average precipitation over the course of a year. We're going to do actually a group by of the result of this. So this individual function, the zonal stats, is going to give us summary statistics for just 1 year, but we're interested in the sum of that average. So summing up the average of each month for the whole country. So we're going to do that in a group by. So we're going to group by the name of the country, summing up the average precipitation for each country. And then we need to wrap the any value, we need to wrap the country's geometry in this any value function here, because we're doing a group by, and the geometry is going to be for the country is going to be the same for each of the 12 months. So we just care about one of the values for our geometry. Okay, so that gives us a table like this. So these are the rainiest, or the countries that receive the most precipitation. And then it might be useful to visualize that. So we can visualize that in Sedona Kepler. And we can style this. Let's go in here. We'll turn off stroke color, and fill color will be based on yearly average precipitation. We'll change the color scheme to something, yeah, this one, I guess, is good. Maybe the green one. Yeah, the blue one represents water precipitation. That's probably better. And we can see, okay, this makes sense, right? So the most precipitation is occurring in tropical countries along the equator. Intuitively, that makes sense. So Colombia is high on our list. Indonesia is high on our list, and so on. So that makes sense. So here we're seeing where the highest average yearly precipitation occurs as the result of a zonal statistics operation by joining our vector data, so the polygons of each country, with our raster data about precipitation. So that's quite neat. Let's move on to the final example that I have prepared for us, where we're going to take a look at tiling rasters. So far, we've been working with fairly large raster. In the previous one, we had 12 rasters, but each one represented the entire surface of the Earth. Typically, if we have higher resolution data or larger rasters, we want to tile up those raster data sets so that we can more efficiently operate on them in parallel, rather than working with one large raster at a time. So we're going to look at a data set from NOAA. This one I think is quite interesting. This is a data set of nighttime visible lights. So this is derived from satellite data, and essentially, where on Earth are we seeing what intensity of lights? And this is useful for determining, okay, what are the populated and developed areas? Cities are going to have brighter lights. But it's also some of the derived data from this, I think, is really interesting. So estimating GDP as a result of looking at this nighttime light data to give us an indication of economic activity. Also looking at poverty estimates. This is really useful in parts of the world where we don't necessarily have the type of economic data published. So this is this I think is a very interesting one to look at. We can also look at how this changes over time to give us some indication of natural resource extraction in certain areas. That could be, um, indicative where we see lights increase over a period of time and then decrease. It can be indicative of some larger scale natural resource extraction. So I thought this was an interesting data set to take a look at. So we're going to load this as GeoTiff. First, we'll just take a look at visualizing this uh, as just an image here to give us a sense of what this looks like. So this is the data from 1993, so a little bit outdated, but that's okay. There is more recent data, I think, up to 2020, I think. I just grabbed 1 year though. So here we can see the distribution of nighttime visible lights throughout the world. And we're going to load this using the rs from path function. It's loading a single GeoTiff, and we'll create a view F10 1993. Then we're going to use the rs tile explode function to tile this raster. And what we're going to do is specify the dimensions of each tile that we want to end up with. And we get back with multiple rows. So we've converted our table of a single raster into multiple tiled rasters in a table. And we have an X and a Y that maps to kind of 0, 0 is going to be the tile in the upper left, and so on. So similar pixel coordinates now, but now for each tile. And now we're going to write this this data to a Havasu table. So if you watched the last live stream that we did, we took a look at the Havasu open table format specification. So Havasu, this is the extension of Apache Iceberg that Sedona and Wherobots Cloud uses to store data. So I'm writing this data frame, so our table of tiled rasters, I'm writing that to a database in the Wherobots catalog, and I've called testdb. We're calling this the F10 1993 table. So now I can refer to this by the name of the table in the Wherobots catalog. And again, this is specific to my Wherobots user. And this is just the default catalog. And then I've chosen just to call this testdb, but we could choose a better name for that database. Anyway, so we end up with 11,154 rows, which map to the number of tiles that we have stored that we've generated as a result from tiling our original raster into 256 by 256 tiles. And we can visualize this. So what we did here was we, for each row in the table, we added a column where we computed the envelope, the bounding box for each tile, and then we just visualize that. So this is just the bounding box of each tile. And if we zoom out, we can see how these tiles are split up, and we can see the XY values for kind of like pixel space for referring to each tile. So each tile is now a raster that has the nighttime light data for that specific bounding box. So this data is just a single band. It's just one value that represents the intensity of the light visible at night. We can visualize each grid. So here for our table, we are selecting just the first 5, calculating the bounds, and then visualizing the raster. since these are far up in the upper left, the first few, they're mostly black, not a lot of visible nighttime light in that area, but get a sense of what each tile data each tile contains. If we wanted to look up the value, so the like intensity of nighttime visible light for a certain point, we can do that using the RS values or RS value. This is the RS values takes an array of points. So here we're just passing a single point. So we could also use RS value. But if we had multiple points that we wanted to find values for, we could use this function as well. This time, though, it's a little bit more complicated because first we need to find the tile that intersects with the geometry, with the point that we want to grab the value for. So we do that first to find the tile where the tile bounds intersects with the point geometry. So we use the RS intersects to do that. So that gives us this matched tile that we can refer to later. Now to find the values from that single matched tile that overlaps with our point, we can see that the value is 63. So the light intensity is 63 for this point. Okay, so let's look at another zonal statistic example. And so in this case, what we're going to do is load US counties from a shapefile. And so this is, again, from the Natural Earth dataset. And what we're going to do now is for each county, we're going to perform some zonal statistics. And what we want to do here is first, for each county, find the tiles. So because we have polygon geometry for each county, this could be one or more tiles that intersect with the boundaries of our county. So similar to what we did up here to find the tile that intersected with our points, to be able to find the value at a specific point. But now we're doing that for a polygon geometry. So we could end up with multiple tiles. And again, we're going to do the zonal stats operation. So for the matched tile, that's our raster, and the geometry of our county, we're going to calculate the mean this time. And again, we're doing a group by. So again, we're going to wrap this in a sum. So we're kind of calculating the sum of the averages of each pixel for each county, which I think is what we want here. Because essentially what we want to know is something like, for each county, what counties have the most visible nighttime light, essentially, is what we're looking at here. And so we're summing the averages of each pixel to kind of extrapolate that across the county. Now, county might not be the best geometry for this zonal stats operation in this case. Maybe it's a bit too coarse. Zip code might have been a better one, or maybe even parcel, something like that. Anyway, so what we're going to end up with are the sort of average light for all of the pixels for each county, and we're grouping by FIPS. FIPS is a code that's used to refer to counties and states in the US. I'm not actually sure what that actually stands for, but I think typically in a FIPS code, the like the first two countries for US, for the first two characters, US for the country. And then I think the next two are state. So whichever state is number one in this case. And then I think the next three are the county, something like that. Anyway, so we end up with a table like this. So we have the geometry of the county. We have the FIPS code, which is like the unique identifier for a county. And then we have the mean light intensity for, which is the average of pixels throughout the county. So we have a table like that, and then we're going to visualize that. One thing that I realize I do frequently is I forget to cache the sort of intermediate representation of the data. So notice here that we have our SQL statements, and then we materialize it by calling the dot show. So when we call dot show, that's actually what triggers the execution of this SQL statement. And what we can do is after we run this, we can call dot cache to cache the values of the data frame. So then they're immediately available for our visualization. If we don't call cache, then we're essentially just running that query again. Anyway, that's fine. So let's visualize these results now. So in Sedona Kepler, we can go in here to style the visualization, and let's turn off the stroke color. That makes things a little busy. And for fill color, we're going to say we want fill color to be based on this mean light value. And I don't know, this sort of white to green intensity. Maybe that's a good one. So this gives us some indication now of the light intensity at night for each county. So if we want to move somewhere that has not a lot of light at night, you can see where to go. And this, this roughly maps to populated areas, right? So major cities are going to have much more visible night light. Cool. So that is another example of kind of this idea of joining vector and raster data together, performing some statistical analysis of that data. In this case, looking at nighttime lights. Well, we're a bit out of time. What I thought would be interesting also with this data would be to look at changes in time. So this specific data set that we tiled and then computed zonal statistics for was just 1 year, but we have multiple years throughout time. So there'd be a few different ways that we could compute that. One would be to use the map algebra function to actually, for each pixel, to compute those changes. Since the map algebra function, when we were using it, we used it for multiple bands within the same raster, but we can also use map algebra function across multiple rasters, in this case, which would represent time series data. So quite neat. So pretty powerful, the things we can do with working with raster data in Sedona. Great. So that is just about all the time we have today. One thing I would like to show, which is one example, and you can find this on GitHub. I'll drop a link to this notebook in the chat as well. But today we were loading raster data ourselves. We don't always need to do that. We can also take advantage of the Wherobots Open Data Catalog, which includes data sets that Wherobots has curated from public data sets like building footprints, Landsat, surface temperature data, OpenStreetMap, weather events, these sorts of things. And so this example I think is quite neat. It's combining a few different vector and raster data sets for insurance analysis. So in this case, combining data about wildfires, weather events, uh, zip codes, and then the raster data set is Landsat surface temperature and looking at calculating surface temperatures per zip code, combining that with incidents of extreme weather and wildfire. Here you can see the use of map algebra to convert Kelvin to Fahrenheit in this case. And then we join that on each zip code combined with some of the areas prone to wildfire to find areas that are prone to hot weather and more extreme weather events. So I thought that's an interesting use case that kind of puts a more use case specific focus on working with, especially in this case, large scale raster data set, since that Landsat surface temperature data set is quite large. But anyway, that's available in the Wherobots Open Data Catalog, which if we go in the documentation, find here, the Wherobots Open Data Catalog. So this talks about just some of the data sets that are curated and available. I'll drop the link to that in the chat as well. Great. Well, thanks everyone for joining today. That puts us at the top of the hour. So hopefully that was useful just to take a look at what we did. And again, the link to the code for this notebook is on GitHub. But we reviewed raster data, kind of comparing raster data and vector data. We took a look at how to load raster data specifically as a GeoTiff in Sedona in Wherobots Cloud. We saw how to use map algebra to calculate the NDGI, so a measure of sort of vegetative index to determine land cover. So how we can work with multiple rasters, looking at global precipitation data, and then zonal statistics to calculate precipitation by country. And then we saw how to tile large rasters for more efficient computation on our rasters using a data set of nighttime visible lights. And then we saw how to join that raster tiled data with vector data for counties to get a measure of the nighttime visible lights for each county. Great. Well, thanks everyone for joining today. We're gonna call it quits there, but let us know in the comments what you think, what other types of data sets or other types of geospatial analysis that you would like to see. And as always, we will see you again on the next iteration of the live stream. We're doing one of these per month. So we'll figure out, based on folks' interest, what topic to cover next. So definitely let us know in the chat what type of data you'd like to see. And as always, if you'd like to follow along, feel free to create a free Wherobots Cloud account at wherobots.services. So thanks a lot for joining, and we'll see you next time. Cheers. Bye-bye.